So last class we left off with this example, writing a nuclear equation for alpha decay. And the most important thing, or one of the most important things when we're doing these decay equations, is figuring out what our initial nuclide is, the mother nuclide, and then figuring out what type of decay we have. In this case, it tells us we have alpha decay, and so we write our alpha particle. You will need to know several types of particles. So writing our particle out on the product side, and then doing a little bit of algebra with our mass number and our atomic number to figure out the mass and atomic numbers for the daughter nuclide, in this case, lead 212. Otherwise, they're not terribly difficult. You don't even necessarily have to do these little, find what x is, find what y is, if you can do that in your head. So those are pretty easy. So alpha decay is when we are losing a helium nucleus, because we don't have any electrons along with it. Alpha decay is our big boy for radioactivity. It's our biggest particle in radioactivity, and it behaves kind of like a semi-truck in traffic. We're using car analogies for the sizes, and we're thinking about them in traffic. At least I'm thinking about them in traffic. So this is our 18-wheeler, our semi-truck. It's got the most mass. It's the biggest thing that you're likely to see on the road unless somebody's hauling something really large. It's got the highest ionizing power. It does the most damage when it crashes, is basically what that means. Most likely to form splinters of cars and other vehicles. However, it has the lowest penetrating power, most easily stuck in traffic. If it goes rogue, if the brakes get cut on an 18-wheeler truck, it won't go very far before it's stopped up because it's just going to run into things constantly. It's too large to navigate its way around other vehicles. And so that's what we're thinking about in terms of penetrating power. It's not going to get very far before it runs into something. The ionizing power is the ability for this radiation to turn other things into ions. So stealing electrons or popping off parts of a molecule or an atom or fracturing it. In living organisms like us, this can cause damaging chemical reactions like cancer, or it'll just kill cells or disrupt their functions in some other way. The penetrating power is the ability of radiation to penetrate or pierce, infiltrate, burrow into matter. So the further it can get into your cells, your body. Our bodies, for the most part, have a nice outer layer called skin. Skin protects us from solar radiation. So if you go outside, you don't immediately die from the UV radiation. You might rapidly deteriorate because of UV radiation, depending on your genetics, but you're not going to immediately die. You won't immediately see negative harmful effects. You can survive for probably at least 30 minutes in direct sunlight without breaking down into whatever you would break down into. And so that's the sort of thing that's going to be stopping the radiation. And so alpha decay, because it's got this large size, it's bigger than our other ones, like a semi-truck in traffic. Because it's so big, it'll run into something sooner. So it'll hit our skin, and our skin, because it's kind of got layers to it, it's going to hit our skin, it's going to stop moving. It's not going to get into our sensitive bits. So it runs into our skin and gets stopped. And if we haven't exfoliated in a while, it's just hitting dead skin cells, and so that doesn't even matter at all. Or it's hitting stuff that's going to be replaced soon enough if it's outside of our body. If it gets inside of our body, where all of our sensitive bits are, then because it has really high ionizing power, it's going to do a lot of damage relative to some of our other types of radiation. So if it's outside of us, not a big deal, but if you accidentally ingest it, it's a bigger deal, much bigger deal. Beta decay is our next form of radiation, and I don't know why, but these are supposed to be connected. In beta decay, an unstable nucleus emits an electron. Our beta particle is just an electron. And for reasons that we don't really talk about in this class, we just say that this is how it is. When an electron, our beta particle, is emitted from the nucleus, that makes a neutrally charged neutron turn into a proton. So it goes from having 0 charge to having a 1 plus charge because of the 1 minus charge that was emitted. And it works out for our little equations that we do. So 88 equals 89 minus 1. That's true. So a neutron becomes positively charged. Possibly the hardest part of the different types of decay is just memorizing what the different types of decay are. Our beta radiation is smaller than alpha decay. Smaller than alpha decay, or alpha particle. Right, our alpha particle was a helium nucleus, so 2 protons, 2 neutrons. Protons and neutrons are like 2,000 times the size of an electron. So we're like 8,000, 9,000 times the size for an alpha particle versus just one single electron. For cars and traffic, our comparison is a 4-door or 2-door sedan. So just like a regular car, not an SUV, not a motorcycle. They're way less massive. I'll just say 8,000 times smaller in terms of mass. So they've got way less ionizing power. If you had the choice of being hit by a semi-truck or a sedan at the same speed, I'm going to pick a sedan. That's one of those situations you hope you never get into, but if you had to choose, pick the smaller vehicle because it's less likely to kill you. So it's going to have lower ionizing power. It doesn't hurt as much when it crashes. But it has higher penetrating power. If you're driving a 4-door sedan and somebody cut your brakes and you're driving 70 miles an hour on the highway and there's stopped traffic suddenly, you've got much better odds of not running into somebody until you've had time to coast and maybe pull your e-brake, which hopefully works. I don't know if that works that way. But you hopefully have some time to crunch your engine before you run into something because you're a much smaller vehicle. It navigates traffic a little bit better than our semi-truck, our alpha particle, because of its size. So since it's smaller, it can slip between the crevices. It's got more opportunity to not hit stuff. It can make its way through smaller gaps. It can be stopped, for example, by a sheet of metal or possibly a thick piece of wood. This makes beta decay a little bit more dangerous if it's outside the body, because it's more likely to pass through your skin without getting stopped and get in and damage your sensitive inside bits. But if you ingest it because it does less ionizing damage, or it has less ionizing power, it's going to do less damage compared to alpha decay. So not as big of a deal if you have it inside of you. Still not great, but not as bad. Our third type of radioactivity is gamma rays. Gamma rays are a form of electromagnetic radiation. They're the very highest energy end of our electromagnetic spectrum. So they are high energy photons. They don't have any charge, they don't have any mass. And they're usually emitted with other types of radiation. Our symbol for a gamma ray is this gamma symbol with zeros, since it doesn't have any mass or charge. So in a way, it's like the easiest of the radioactivities. So these usually go along with other types of radiation. For example, this one's paired up with an alpha particle. So uranium-238 can decay to thorium-234 by emitting an alpha particle, and when it does that, it also has extra energy that it needs to get rid of in the form of gamma rays. Gamma rays are the motorbike, the motorcycle of radioactivity. Again, thinking of the question that you hope you never get asked, which would you rather get hit by? A motorcycle, a sedan, or a semi-truck? You should pick, they're all going the same speed, by the way. You should pick a motorcycle. If you want to get hit by a vehicle and live, take the least amount of damage, a motorcycle is probably the best option, assuming that the force is well distributed over your body, because that could be a difference with a sedan and a semi-truck. It's the least likely to, ruin your life. So lowest ionizing power, if you get hit by a motorcycle, maybe if you're driving a car, then it makes a little more sense. If you get hit by a motorcycle, your car's probably okay, reasonably fine. Motorcycles do, however, have the highest penetrating power. You will often see motorcycles just driving between the lanes. So if for some reason your brakes went out on a motorcycle, you're probably fine. You just coast to a stop. It'll be a little scary, but you should be fine. Versus a sedan, you probably hit something. Just get into the median. So gamma rays go through lots of stuff. Like you have to go out of your way to put the materials in place to stop gamma radiation. It'll probably just go right through you. And so they can be stopped by several inches of lead shielding, or appropriate levels of lead shielding. If you work with stuff that has gamma ray emission regularly, usually you'll have lead bricks so that you can build your own little brick walls, and you'll have lead infused glass, which has a yellowish tinge to it. You might even have a special fume hood that has that lead infused glass in it, so you can still see through it and you can work safely in a fume hood. I've worked with a little bit of that. It's kind of cool, but then also you have to check yourself to make sure you don't have radioactivity on you.
Why does lead prevent this stuff from penetrating?
Lead stops it because it's really dense. And I think lead is typically used because it's cheap for how dense it is. There's probably other things that would work really well too, but lead is just so easy to get your hands on, relatively speaking. You wouldn't use tungsten. Tungsten would also be super heavy. But yeah, there's other stuff that would work. It's just that lead is cheap. Cheap and thick, dense. You can also stop it with concrete. So if you don't need it to be portable, you can use a lot of concrete. So like there was a reactor in Japan, I think, that had a meltdown, and they like sunk the reactor into the ocean and then covered it in a big dome of concrete. Something like that. So concrete is like a good choice if you're covering up a big radioactive site, which hopefully none of us have to do. So that's our third type of radioactivity. Our fourth, and not final, surprisingly, is positron emission. Positron emission is the antiparticle, the opposite particle of the electron. So it's basically an electron, but positive. It's a positive electron. If a positron and an electron collide, they annihilate each other. So they just poof, they're gone. Or something like that, and then they release a bunch of energy as gamma rays. In positron emission, this is the opposite of beta decay, sort of. In positron emission, a proton is converted into a neutron, and a positron is emitted. So for beta decay, it was a neutron goes to proton plus an electron. And in positron, it's, shoot, I got these backwards. It's the other way. And it's the same symbol. It's the same E as electron, but it's a +1 charge instead of the -1 charge. So it's like a sort of opposite. It's the protons and neutrons parts flipped, the charges flipped. So that's positron emission. When an atom emits a positron, its atomic number decreases by 1 because we're turning the proton into the neutron. The mass number stays the same. But atomic number decreases by 1. And it's got the same size and pen as beta decay, beta particle. And then our last radioactivity type that we're going to learn about is electron capture. Electron capture happens when a nucleus, where the protons and neutrons are, assimilates, aka absorbs, an electron. Absorbs/captures an electron, as the name implies. And the net effect is that a proton is converted into a neutron. Since the proton has positive charge, the electron has negative charge, it makes sense, at least in terms of charge, that it would turn into a neutron. And this is the true opposite of beta decay. Since beta decay was getting rid of an electron, and this is gaining an electron. So the net effect is the atomic number decreases by 1. So ruthenium 92 turns into technetium 92, for example. And then here's a convenient table from the book that's got those 5 types of radioactive activity. Do we have any questions about our types of radioactivity? Okay. Write 3 nuclear equations to represent the nuclear decay sequence that begins with the alpha decay of uranium-235, followed by a beta decay, and then another alpha decay. There's the alpha and beta particles in case you had forgotten. So the information that we would start with here is we're starting with uranium-235. That's our overall parent nuclide. So uranium, and the mass number is that 235. Since it's uranium, it has the atomic number of 92. We can find it in the F block, the actinides series on the periodic table, down below the rest of the periodic table. And that's going to undergo alpha decay. So we can write in, on our product side, our alpha particle. And then we need to figure out what our daughter nuclide is. We need to figure this out before we start the next part because we're going to use this daughter nuclide in the next nuclear equation. We could write out a little equation for ourselves if we want to. 235 equals x plus 4. A little bit of quick maths, and you'll find out that it's 231. And then 92 equals whatever the atomic number is of our daughter nuclide plus 2. So it's going to be 90. 92 minus 2 is 90, and so that's TH, thorium. So thorium-231 is what we're starting the next nuclear equation with. And this time it's undergoing beta decay. So it's emitting an electron. And since our electron has no mass number, or a 0 for a mass number, that means that our mass number is still going to be 231. All that's changed, separate these, all that's changed is our atomic number. So 90 equals Y plus -1. We would figure out that it's 91. So we've moved up 1, and PA is the symbol that corresponds to that. I think that's protactinium. And then we would start off our next nuclear equation with that. So 231 over 91 PA undergoing alpha decay. So write in another alpha particle, and it's 227 and 89 for our numbers. So this is AC, actinium, I think. So for this, the beta decay one, the equation that we'd write out is like this, that 90 equals Y minus 1. Yeah. And so then if you rearrange it, it's Y equals 91. just making it balance out. Other questions? All right, we can practice for positron emission and electron capture as well. So write a nuclear equation for positron emission of sodium-22 and electron capture of krypton-76. All right, so we can start off with our positron emission. The positron is the antiparticle of the electron. So it's got the opposite number. It's got a +1 instead of a -1, and it's still got the symbol E. Sodium-22 has a mass number of 22, and we can find it on the periodic table. It's got an atomic number of 11. So it's emitting a positron, going to something and a positron, 0 and +1e. The top number doesn't change, so that's easy. And then the bottom number, 11 equals some number +1. That number, of course, is 10. And so this would be neon, 22. We can write a similar nuclear equation for the electron capture. Capture here being absorb. So we're absorbing an electron. That means the electron goes on the left side with our krypton. So krypton-76, we find the atomic number on the periodic table. It is 36. Add to that our electron. The top number doesn't change, so it's 76. And the bottom number, 36 minus 1 equals 35. So this would be bromine. So there's that. You might be wondering, why are nuclides radioactive? You're probably not, but you might be. Why are they different types of decay? Well, it turns out a nucleus is a collection of what we can call nucleons. So nucleons are just things that are in the nucleus, protons and neutrons. And they're held together by the fundamental force of physics, the strong force. There's also a weak force, but the strong force is what holds them together. So the strong force keeps nucleons together. And I can't remember if this is one of those things that you can explain or if it's just that's the way it is and that's what we call it, because that happens sometimes. I'm sure that Wikipedia or the internet elsewhere could probably tell you. So some things are happening in our nucleus. Our nucleus, being a collection of protons and neutrons, is positively charged. You may know if you've played with magnets very much, positive parts tend to not like to go together very much. If you put a bunch of positive ends of the magnets close to each other, they repel each other. If you get the positive ends of the magnets and you stick them onto like just a random piece of metal, they'll usually stick on, but if you get too many of them on there, then it's too much positive charge and then they'll all pop off. So that's what comes to my mind when I'm thinking about this, because I like magnets and playing with magnets. So the stability, whether the nucleus stays together, is a balance between the repulsive Coulombic force between protons. The positive charge repels positive charge. Right, so the protons are repelled by each other. But there's also an attractive, strong force that holds all of the nucleons together. And so there's a balance there. If you've got too much positive charge, the whole thing's going to fall apart. And if you have too many neutrons, the thing will probably also fall apart because there's not quite enough of that attractive strong force keeping things together. So there's a balance of protons to neutrons that you can have that will be stable in a nucleus. Too many protons, it's unstable. Too many neutrons, it's also unstable. Neutrons are helpful because they attract the other nucleons. If we're thinking about magnets, they attract the protons. They probably also attract neutrons. And they don't have any of the repulsive force that comes along with having charge, positive charge. There are energy levels for protons and neutrons. I'm just going to say nucleons because it's shorter. So we know, hopefully you remember, electrons have different energy levels within an element, within an atom, that they'll fill up based on where they are on the periodic table, the 1s, 2s, 2p, etc. There's also a similar thing for our nucleons, our protons and our neutrons. The way that we can, we're not really going to talk about the energy levels very much, I'm just mentioning that it exists. The way that we can predict whether something's going to be stable is based on empirical evidence and the ratio of neutrons to protons, n over z. Can anyone think of a country that has, if you initialized it, would be NZ?
New Zealand.
New Zealand. NZ. New Zealand. It's probably supposed to be capitalized. Oh well. You can plot the number of neutrons versus the number of protons for all known nuclei. So our y-axis on this graph is the number of neutrons. Our x-axis on this graph is the number of protons. And we've got these yellow dots. It's like a big grid. The yellow dots represent a lot of the known nuclei that exist. And the green dots, right, in this like little middle bit, those are stable nuclei, meaning they don't undergo radioactive decay. The ratio is from about 1 to 1.5 n to z. So neutrons per proton. And our largest Z number is 83. You can't get a stable nucleus above 83, which is bismuth. The reason that I mentioned the NZ thing is because the shape of this kind of looks like New Zealand. So that might be a helpful way of remembering that it's n over z instead of z over n. It's the n to z ratio because the New Zealand ratio. This is called the Valley of Stability or the Island of Stability. And the way that we use it is by comparing the n to z ratio. So if it's too high, meaning that we're above, like if we were up here, we're above the Valley of Stability, the Island of Stability. We're above New Zealand. This is going to be really unstable because we're outside of the stable zone. And so what needs to happen is we need to move down on our chart. So this is if NZ is too high. We've got too many neutrons. We need to reduce the number of neutrons that we have. We might also increase the number of protons that we have. And so this is going to undergo beta decay, since beta decay converts neutrons to protons. if our N to Z ratio is too low, for example, if we're at this blue dot, then we would need to increase our number of neutrons relative to our number of protons. We need to go up on the chart, or go left on the chart, or just generally move towards that yellow zone. So we have too many protons or not enough electrons. Sorry, not electrons, neutrons. And so there's two ways that we can make more protons. We can either do a positron emission or an electron capture. You can also do alpha decay because it changes your N to Z ratio. You're losing the same number of each, but because they're both getting smaller, it changes the ratio. But it's got a really small effect, and so we wouldn't expect alpha decay to be a common or an effective way of increasing our stability. Question?
Why is having a high level of neutrons really high for radioactivity when neutrons don't have repulsive force? I think it's related to the energy level thing. Like there has to be a good balance. If you've got too many of them, I think that there's not enough strong force, and so they just start to fall apart. I'm not sure exactly on the reason. The way that I would think about it in my brain, thinking about them is like magnets and not magnets, is if you've got if you've got a couple of magnets and a lot of things that aren't magnets, right? Like if you've got paper clips or something, if you get too many paper clips in there, some of them are going to start to fall off because there's not enough of the charge from the magnets. I don't know if that applies to this, but it certainly works as an explanation, whether or not it's true. So like the protons, having a lot of protons doesn't, like the neutrons being converted to protons?
That's because we've got too many neutrons, so it's unstable. And so by converting, getting our ratio back into this stable zone, we've got more of that attractive force. That's like adding more magnets and taking off some of the paper clips, increasing the amount that it sticks together. You could overcorrect. Certainly, like if we were just playing around and we had that power, you could certainly overcorrect and then have not enough protons, and then it would come back to balance.
So like in a perfect scenario, we would have equal protons and neutrons?
Not equal. There's like a different numbers of ratios. So like at small numbers, small things, our N to Z ratio is 1. As we get to larger stuff like zircon, it comes up to a 1.25 ratio, and then way up here with mercury, it's 1.5. So it's somewhere between 1 and 1.5 that we find most of our ratios for stable nuclei. But you certainly wouldn't want a neutron to proton ratio less than 1. Other questions? I don't expect you to have the graph memorized. You should know like kind of the general shape. And if I give it to you on an exam, you should know how to use it, even if it's like just like unlabeled. Okay, so if we want to predict type of radioactivity, we can consult the graph of New Zealand, our N to Z ratio, and kind of pick where we are for whatever nuclide we have. Look at how we would need to change to get to our island of stability, either going down or going up.
We could also compare the mass number of the nuclide to the atomic mass that's on the periodic table. And because our atomic mass is the average of our stable nuclides, that's like about an N to Z ratio that should be about right. So like if we look at our nuclide ruthenium-112, the atomic mass of ruthenium is 101.07. So that would represent a stable N to Z ratio. Somewhere around there should be stable for ruthenium. So ruthenium-112, since it's still ruthenium, means that it has the same number of protons but a different number of neutrons. So more neutrons than is stable need to reduce number of neutrons, since that number is bigger. If the number was lower, then we would have too few neutrons. That would be the other side of the thing. More likely, we'll be using this lower method on an exam, if I had to guess. I shouldn't have to guess, but I am. You should also know how the value of stability works. They're the same idea, it's just that one presents it graphically. Okay, let's predict type of radioactive decay for each of these. We've got lead 192, lead 212, xenon 114. So for lead, PB 192, our lead atomic mass from the periodic table is 207.2. This means that we're stable around 207. It's not necessarily 207. It could be that like 208 and 206 are stable and it just averages out to 207. But we would want to be kind of in this ballpark of 207. So then we want to think about how does PB 192 need to change to get to 207? What needs to happen? We need to increase our number of neutrons. Our neutron count is too low. To increase the number of neutrons, do we need to go through beta decay or positron emission? Yeah, so we need to go through positron emission or electron capture. And if you got confused and you forgot which one does which, as long as you remember what the particles are, you could just write out your equation. That's what I would do if I got confused, if you don't have them memorized, or if you just want to double check. positron emission will make more neutrons by losing protons. That'll affect our N to Z ratio. How about for lead-212 and xenon-114? For lead-212, the lead atomic mass is still 207.2. (212) is above 207. Need more protons. Or fewer neutrons. So we're going to do the opposite process. This will be beta decay. And then what about for xenon-114? Xenon on the periodic table is 131. 114 is below 131. So we need more neutrons or fewer protons. So this is going to be another positron emission. Questions? All right, also related, we have these so-called magic numbers. So it's not just the ratio that's important. The actual number of protons and neutrons also matters. A large number of stable nuclides, aka non-radioactive nuclides, have both an even number of protons, our protons here being Z and our neutrons being N. And we've got pairings of both being even, one being even, the other being odd, and both being odd. We've got the most stable nuclides with an even number of protons and an even number of neutrons. Only 5 stable nuclides are known which have odd numbers of protons and neutrons. Nucleons tend to pair together like electrons pair together. So this is, I talked about this earlier, our nucleons also have energy levels within a nucleus, like our elements, or electrons, sorry, have energy levels in an atom. So atoms with certain numbers of electrons are uniquely stable. That's our noble gases, right? Our noble gas configuration for electrons is especially stable. Unfortunately, our magic numbers are not quite as easy. So our magic numbers, our stable numbers for protons and neutrons, are also especially stable. And those numbers are here. So for our neutrons or our protons, the numbers 2, 8, 20, 28, 50, and 82. Those are our magic numbers. And for neutrons, 126 neutrons is also especially stable. The magic numbers are all even numbers. There's no odd numbered magic numbers. There's probably a good way to remember these numbers. I have no clue what that good way of remembering them is. It probably exists. If you find it, let me know. But otherwise, maybe it's a phone number.
And what do they represent again?
These are stable, especially stable numbers of protons and neutrons. So for 2, helium 4, a regular version of helium, has 2 protons and 2 neutrons. So it's got the double magic numbers. It's especially stable, which is also just true. If you had something that had 8 and 8, that should also be really stable. That would be like oxygen. Should be especially stable, I guess. Basically, if you have either of these, any of these, like for your protons and neutrons, that should be a stable nucleus, or a more stable nucleus if you've got any of these magic numbers for your protons or neutrons.
So you're kind of just looking for that as like the atomic number, or more specific?
Yeah, so any of these for atomic number, they're going to have this number of protons.
Yeah.
And then you can also have like different configurations with the number of neutrons that would be more stable. So like lead has the Z of 82. So that should be especially stable, and it is.
Okay.
We did a little bit of radioactive decay series earlier. You can draw out really long radioactive decay series. All atoms with a Z of greater than 83, so if they're past bismuth on our periodic table, they're radioactive. I don't know why I wrote that. Past, anything past bismuth on our periodic table is radioactive. All of it, 100%. They're going to decay in a bunch of steps, mostly alpha and beta decay. And then if we've got some extra energy to get rid of, that's where gamma decay comes in. And this will continue, the radioactive decay will continue until stability improves. So once you reach a stable nuclide, then it stops. Sometimes they will overshoot. So for example, if we look at the bottom of this chain, we've got some things that have TL in there. TL is 81 on our periodic table. And then it pops back up to lead, and then maybe it's a lead that's not stable, and it goes to bismuth, and then it either goes to polonium or to TL again. So it can bop around kind of in that upper range. So not all lead is stable, but it will eventually, lead's a common ending point for these nuclide decay series. But there's a lot of decay that goes on. You wouldn't be able to predict the type of decay, probably for the most part. That's not something I'd expect you to do. I also wouldn't ask you to like write out all of the nuclear equations for this decay series, for example, because that's just like a pointless waste of time and energy. And I don't want to grade that.
So is bismuth also radioactive, or just things past that?
Bismuth is not always radioactive. It's things that are past it. A lot of bismuth is actually stable, and you can, like somebody I went to undergrad with makes art that involves bismuth because it makes really cool crystals. So it like melts at a relatively low temperature, and then it forms into crystal structures, and it forms a bismuth oxide on the outside that's like polychromatic. It's really cool. Yeah.
It's like the pyramids and stuff.
Yeah, exactly. But it's stable, or at least you can get it in amounts or in isotopes that are stable. There's a lot of stable bismuth. There's a bunch of ways to detect radioactivity. One of the ways to detect radioactivity is you can wear these little dosimeters, so like badges. And if you work around radioactivity, typically you would have one probably like on your person, so like on your chest. And then you might also have one like on a hard hat or something, depending on where you work. You might have 2 or 3 of them. And they've got a reaction that goes on inside of the dosimeter. There's also film badge dosimeters, which I'm not sure if those are a different thing than this. Basically, it's just like a piece of film, or in this case, like crystals that you wear that react with the radioactivity. And it basically like develops the film or develops the crystals over time so that they change color. And then you would submit them like at the end of the week or the end of the month. And then they would get processed, and they would figure out based on the color or based on how developed the film is, how much radioactivity you were exposed to. This is a way of tracking your exposure. To make sure that you're not exposed to really high levels of radioactivity that could end up causing you to develop cancer at a higher than normal rate or a much higher than normal rate. The people at OSHA have like regulations and limits on the amount of radioactivity that you can be exposed to over a certain period of time. So this is a way of checking that kind of over long periods of time. There's also ways of detecting them for shorter periods of time or like instantaneously. The most famous being the Geiger or Geiger-Müller counter. This is the one that you probably know about, the one that goes click, 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 click. Or has like a buzzing, beeping sound. If you've played Fallout, this is the one that, the clicking that you're hearing when you're playing Fallout and you're exposed to radioactivity. And it's a handheld device. They probably don't all look like this, but this is all the ones that I've seen in that picture. And basically you just have a gas trapped in the little handheld rod thing, and it reacts and produces an electrical signal when it gets radioactivity in it. And then you've got an amplifier, and there's like a settings knob, like a sensitivity knob there. So you can have it really low sensitivity, really high sensitivity, depending on like the circumstances that you're in, and then it just changes. There's a little readout on this graph, and then there's also optionally the clicking or the beeping noise. When I was working with radioactivity, I had to use one of these to check. I'd like have to scan my whole body to make sure that I didn't pick radioactivity up with me. Because if I did, like if you get radioactivity on the bottom of your shoe, and then you go walking around the hallway, then the whole hallway's radioactive, and they won't want that, because then that's like a whole worker exposure thing. So I got to do that every time I was playing around in the radioactivity lab. And by playing around, I mean doing very serious work, of course. Another way of detecting radioactivity is a scintillation counter. I've also played around a little bit with a scintillation counter. This is typically going to be in some sort of benchtop instrument. So this is not a handheld device. This also measures radioactivity in real time. And so you're going to have your radioactive emissions that pass through some sort of material. They'll emit UV or visible light when those energetic particles go through them. And then that light can be detected and turned into an electrical signal that can be read out on an instrument. There was probably a handheld version, but the one that I used, the scintillation counter that I was using, was a benchtop thing. Not super large. I don't think they're terribly expensive either. But who knows? They could be $300,000. It's not that expensive for lab instruments. Okay, what happens in radioactive decay? The kinetics. We've learned about kinetics. Remember kinetics? We're doing kinetics again, just a little bit. So radioactivity is natural. It happens in our environment. You are exposed to radioactivity just like going about your daily life. There's radioactivity out there. It's not that big of a deal. It's probably giving you a little bit of cancer. It's really not that big of a deal. You're getting a much smaller dose just walking around compared to like one scan at the hospital. Everything that's got more than 83 protons and some with fewer than 83 protons are unstable, and they're out there in the world. Radioactive nuclides persist in the environment because new ones are constantly being formed, either from the decay of something else that's really long-lived, or it's being regenerated. From something bigger or generated in the atmosphere, for example. Or elsewhere. Elsewhere. So, since they're radioactive, they must be coming from somewhere, or they would have all decayed, or they're just very, very long-lived, is the other option. It was produced one time, and it lasts forever. All radioactive nuclei decay via first-order kinetics. It's all first-order kinetics, which is nice. We don't have to worry about zero order. We don't have to worry about second order. All first order. So we're only going to be using the first order kinetics stuff. And that makes the math part, at least, I think, quite a bit easier. So it's all first order kinetics. Half-life, we've used before. It's the time it takes for half of the parent nuclide to decay to the daughter nuclide. And we've got this familiar equation we've seen before. If I'm remembering correctly, the top is natural log of 2, 0.693. So we will be using this equation. I'm expecting that it'll still be given to you on the exam. Nuclides that decay quickly have short half-lives and large rate constants. Nuclides that decay slowly have long half-lives and are considered less active. Low activity, high activity, low amounts of decay, high rates of decay. So we'll use that T1/2. Thorium-232 has a half-life of 14 billion years. So that could have just been generated one time, maybe at the Big Bang, and then like a lot of it would still be around. 14 billion years, that's a long time. So if we start with 1 million thorium-232 atoms, after 14 billion years, it gets cut in half. After another 14 billion years, half of those atoms are used up. They've undergone radioactive decay. So we would be left with 250,000 thorium-232 atoms. As a reminder, a radioactive sample does not decay to 0 atoms in 2 half-lives. It gets cut in half sequentially. Every half-life cuts the amount in half. And the rule of thumb that I was taught was that after about 10 half-lives, it's considered to be gone. So if I got radioactivity on my clothes when I was working in that radioactivity lab, we would either just throw away the clothes, basically, or they would hold on to it for, the half-life was like 30 days. So they would hold on to it for 300 days, and then I could have it back, because then it wouldn't be radioactive any longer. So it's basically like just throwing it away, because like I'm not going to come back in 300 days and collect my stuff. I'll be long gone. So about 10 half-lives. I don't expect you to know this. It's just kind of for fun. 10 half-lives, and the radioactivity is gone. And 10 half-lives isn't so bad if you've got like radon 220, which we've got here on the bottom, where it's a 1-minute half-life after 10 minutes. Okay, the radioactivity's gone. Kind of hard to do stuff with radon 220. But if it's thorium-232, I'm not sticking around for 140 billion years. My bones will be gone before then. So depending on the nuclide, you could be waiting forever, or you could be waiting the amount of time that I paused. Some of them are very fast. And this is a graph of showing the atoms of radon-220 and time. This is what a lot of our radioactive decay graphs will look like. It's a natural log plot. And then some half-lives. I don't expect you to memorize half-lives. I'm going to actually tell you here, don't. Memorize T1/2 values. Don't do it. Don't waste your time. You'll be given them, or they'll be in a table in the case of like homework problems. So just check a table or Google it. Questions? Great. We'll pick up here next time.